All right, I'm back. I did manage to finish a little bit earlier than I was hoping. I did manage to finish a little earlier than I was worried that I might have to go to. So that means that from now until about 6, I'm going to try to work on the project. I'm probably going to need a break. I don't think I'm going to be able to do 6 hours straight. So maybe I'll work for a couple hours, take a half-hour break, come back, work for a couple hours. I think, if I'm not mistaken, I just finished. Yeah, this was just finished 9 for the problem set. So I have one more problem set to kind of cover in the first pass. So let me scooch over here and get that set up. And yeah, all right. So I think awfully blue here. I don't know how to adjust see if it's looking a bit better like that. I don't understand at all how this camera light white balance is supposed to be working, because it's been turning blue on me a lot. So I'm going to be doing problem set 10 now. I mentioned before kind of my plan is to get done problem set 10 so that I'll be finished all the main problem sets. And then I'm going to go through all the problem sets again. And from that, I'm going to try to figure out what is the concepts, what are the technical things, what are all the things that I'm struggling with. I'm going to try to write them all down. And then I'm going to kind of make a decision about how I want to handle them. There's sort of 2 cases we can consider for a math class like this. Or are we going to have problems with, oh great, this thing is not focusing now. There's kind of 2 problems that you can have. One is a conceptual problem, meaning that you don't understand a particular concept. It could be sort of a general concept, like, maybe I don't understand operators or hermeticity, or, what makes it a unitary this kind of thing. That could be one of the problems. The other problem could be that I understand kind of how it works, but I'm not comfortable enough with a particular mathematical technique. And so it could be that, well, I understand what, integrating by parts is, but I haven't been doing it very well. So an example of that, where I know already is a weak point, is for me, my dimensional analysis. I've been kind of messing up some things with that, of like, well, what are the dimensions of this, and making sure it cancels and everything works out properly. That hasn't been working out entirely. This last problem I did here, and I was trying to figure out, I had this over like this, and I was like, well, electron volt, we got seconds over a length squared, and that's supposed to be our energy. And I was like, how are we getting that? Because it should be in electron volts, and as far as I know, seconds over length squared is not electron volts. So that's an example of how I need to practice with the dimensional analysis. But it's not that I don't understand what dimensional analysis is, or where it's useful, or how to use it. So both of those things are going to come into play here. This is a difficult technical class, so there's not only issues of concepts of deep fundamental concepts of what is quantum mechanics and how do you answer questions about it, but there's also difficulties of performing the calculations. One of the ones we had for figuring out the fine structure constant, I have it here in pen. This was by far the hardest calculation I've seen in the course in a problem set. I mean, probably computing the actual differentials would have been hard too, but this one involved like a lot of tricks that I wouldn't have been obvious to me to see how to do it that way. So I do think that the problem sets are probably going to be harder than the exam, and they're definitely harder than maybe what I need for my goal. Admittedly, getting an intuition about quantum mechanics is too vague, it's too arbitrary. So one of the reasons I picked a benchmark of passing the exam, similar to the standard I did for the MIT challenge, was just because it makes that benchmark concrete. So although my goal is somewhat vague, I want to have this sort of intuition, and there's obviously varying degrees of intuition and this kind of thing. The sort of goal I'm actually pursuing is something that is actually measurable, something that I can actually work towards. And so I like to do that for a lot of things. So for instance, if you're studying a language, you might have a fluency test or something like that you're doing, as opposed to just, well, I'm just going to get better at this, or you might try to pick some particular benchmark. But that being said, whenever you pick a benchmark, it's also important to recognize how your own benchmark deviates from your actual goal. So even though the thing I'm trying to pursue here is getting myself into shape so that I could pass the final exam for this particular class, I also have to recognize that, being able to perform really tedious technical calculations or doing those kind of things is not so much my goal as I should be able to have some kind of intuition. So I'm more weighting the kind of conceptual end of things of, well, this is true because of some basic properties that I understand about the mathematical structures. Now, I'm not going to split hairs too much on this right now of like, how does this technical benchmark differ from the intuitive benchmark? All I'll say is that I'm going to work as hard as I can on this benchmark, but that if there are places that I'm coming up short, or there's places where I have to make choices about what to invest in, I'm going to go back to how I formulated the original goal. So one of those things I've already decided is I'm not going to spend time learning Mathematica. Not only because I think the full version of Mathematica is a paid thing. I've been using Wolfram Alpha to do some sketching and plots, but I haven't been doing any algebraic solvers or solving really complicated things. And, part of that is just because I haven't been as eager to like learn a whole new technical skill set for that, but also just because that's further away from my intuition or the intuition that I wanted to get from doing this program. Not to say that it's bad, not to say that it's wrong, but just that it's this kind of, okay, and then you put it in and get something to solve it. I'm, to go through the work to do that solution is not as important to me as, okay, well, someone else did the solution. All right, this is what it turns out to be. So I'm going to work on problem set 10 now, which we have right here. And there are 1, 2, 3, 4, 5, 6, 7 main problems. And then I think this 8th problem down here is an optional problem, but I think I'll probably work through the optional problem too, just because I think it'll build on these things. So let's start this problem set, and if I'm lucky, I might be able to get this done even today. If not, I'm definitely hoping to get it done by tomorrow morning. So what do we have here? Well, 0-point energy in a lattice. Consider a particle of mass m. Okay, in a lattice of delta function barriers of dimensionless strength, G0 is much greater than 1, lattice spacing L, and total length D is much greater than L. What is D? Is it the total length of, okay, so we're considering, are these barriers? These are barriers, so it's not walls. Okay, so I gotta put them the other direction. So we're considering this basically. So this is D. This is L. And we have G0 1. And if I recall, what is G0 from that? G0 is the dimensionless sort of strength of the well, which is related to L. G naught should be ML. So it's proportional to, this is not M. The M, the particle M, yeah. This is proportional to ML, like W naught. So for G naught, much greater than 1, what we're saying essentially is that this is a wide, deep well given the particle mass, I believe. So we just have this in the denominator. So it's, yeah, just wide, deep well. Okay. Estimate the ground state energy and compare to a particle confined in a box of width d. So our ground state energy in a box was given by, I think it was 1/2 h bar omega. Not 1/2 h bar omega, 1/2 h bar on omega. This would be this is 1/4. What was it? What was the energy in the finite well? I don't think I have it here. To h bar squared over 2m, and this is m plus 1, which is going to be 0. So this is going to be pi by L squared is equal to pi squared h bar squared over 2m L squared. Okay, that is our square well potential of width d. So this is going to be d. I'm going to change this to d. Okay. And this, we want to estimate what is going to be the lowest energy state. So my guess is that we would have something like, well, we don't have a box on the end of this though, do we? Because these are barriers, so it's not like we're not looking at this, are we? Because that would be the case if it were inside of a box of length d, but I don't know whether it's lattice of delta function barriers. I would guess with these being high barriers, we're going to get something that looks like this, right? The ground state energy is going to look kind of like this. So that'd be my guess with. All right. That is math, yes. I don't understand how it's like this as if the G naught would be relatively weak. But again, it's not in a box. It's there's just delta, so let's see what they have here. Barriers are very strong. In this case, transmission across the barriers is very small. Selections can be parts mostly trapped inside individual wells. Much lower than the value. All right, this is actually right. Okay. This explains an important property of solids. As long as you are looking at chunks of the solid that are parametrically larger than the interatomic spacing, the basic material properties of solid, opacity, conductivity, etc., do not change as you study larger and larger chunks. Note that this would not be true in the absence of the periodic lattice. Oh, interesting. Okay. Well, I didn't get that implication, but it's good to know. Always good to get a question right. Blinded by science. Diamond with a band gap of 5.5 electron volts is a spectacular insulator. At room temperature, diamond sports roughly 10 to the negative 44 times fewer electrons in its conduction band than silicon. Band gap 1.1 electron volts. Diamond is also famously and expensively translucent. What is the minimum frequency to which diamond is opaque? What kind of radiation is this? Curiously, some diamonds are tinted blue. Can you come up with a mechanism that would explain this observation? So let's focus on the first question. What wavelength is opaque to diamonds? So this means we need to go, basically we'd have to take an electron here and excite it over the band gap of 5.5 electron volts. So what wavelength of light has corresponds to 5.5 electron volts? Well, here we can use the de Broglie wavelength. Which is equal to what do I want to do here for angular frequency. H bar. Two pi times this is the frequency or number of times it goes. So this is 1 per second, and we have this times c, which is meters per second, and we should get equals at a wavelength. Hold on a sec. Wavelength. Per second. Divided by speed of light of this. So we want C over V. So our V is equal to E divided by H bar over 2 pi. So our wavelength is equal to H bar is 6.6 times 10 to the negative 12. Jumble 16. 16 eV per second times 3 times 10 to the 8th meters per second divided by 9.5 eV. EVs cancel, seconds cancel, and we should have meters. So we have, that'll give me 1 point. Let's do 6.6 times 3 is going to be 1.98. And we bumped up once, it's 10 to the negative 15 times 10 to the negative 7 divided by 5.5. Let me just do that real quick. So we have 3.6. Ten to the 6th. Oops. Negative 6. Negative 6. Negative 6. It's equal to what? That is too long. It's too long a wavelength. Why did I screw up here? Electron volts. Oh, no. Oh, yeah. 8. Yeah. Oh, I screwed something up here. This is right in terms of dimensions, though. So if I have because it needs to be a lot higher. So if we have 400 nanometers is roughly 400 times 10 to the negative 9, which is equal to 10 to the negative 7. So it has to be, this is smaller than that. This is bigger than that, rather. So this is not right. Because we would expect it to be a much higher frequency than this. Let's see if I get one things right. Am I forgetting a 2 pi here? Oh, I forgot 2 pi. I don't think that makes much difference sometimes. Times 2 pi. Let me recalculate this. So 6.6 times 3 divided by 5.5 times 2 times, I have pi here. That makes it worse. This makes it too big. Let's go over our formula again. E is equal to h bar two pi divided. This would be divided, right? Oh no, 2 pi. Okay, and then our B is equal to, this is in 1 over time. We have meters per second. So it should be C. So we need to divide by C. And this is equal to C times C. Is C divided by this. C is equal to this. That. All right. And so we have, yeah, so what, did I do anything wrong here? So we have our E is equal to and then therefore length is equal to H bar times C divided by E, which is what I have here. Am I forgetting a factor of something else? Okay. Okay. F mid by 5. So let's see if I can recreate that result. So this is equal to 1.3 times 10 to 15 hertz. $230. So no, this is too small. Let's see, 230 nanometers. Hertz. So let's try this. 1.15. 3 times 10 to the 8th. And I have 1.3 is equal to, yeah, it's 2.3. But this is equal to 6 times 10 to the negative 16, 8, 2 times 5, 5.5. So this is equal to 22.6, and then we have 10 to the negative 8. So I must have just done some kind of calculating mistake there to lose that factor, because it is pretty close. So it appears translucent, and then my explanation would be because there's impurities. Okay. All right. 2. Oh, this is 3, sorry. 3. The world is full of fermions. Consider a composite object such as the hydrogen atom will behave as a boson or fermion. Argue in general that objects containing an even odd number of fermions, bosons, fermions. That is an interesting question. So hydrogen plus has I would guess that they act as fermions, but I don't know that. So let's go back to our, if we take the operator, so this is the one where it's a switching operator. I would say that for any number of fermions, it will behave as a fermion. That would be my guess. See if that's right. So we have E1, P1, E2, P2. Oh, okay. So this was not expected. For identical particles and spooky correlations. Consider two variables, x1 and x2. The actual question is whether knowledge of one variable is predictive of the second variable. Such a predictivity is called a correlation. In terms of expectation values, a natural measure of the correlation of two variables is the correlator. Expectation of x1 minus the expectation Suppose we carefully arrange two particles in a harmonic oscillator potential such that one is in the ground state psi naught, the other is in our first excited state psi 1. The following are three wave functions in which our two particles may find themselves corresponding to distinguishable bosonic and fermionic antisymmetric particles. Okay, well, as the expectation of e to the minus x squared to be squared or 2a squared 0 and the 2 I don't know, what do I verify this with? Okay. B, compute the mean squared distance in each of these states and verify that. X1 squared minus 2 x1 x2 plus x2 squared times so this is going to be the expectation of x1 squared minus 2x1 x2 and x2 squared. So this is equal to Ba, ba, ba. So this x1 squared is going to be what? What is the variance of a Gaussian again? I have that. I did that in one of the problem sets earlier. I remember what the expectation, the variance. I was going to search it. 1/2. So we should get standard deviation of that is this. The equation. We get the 2 down here. This is 0. This is just P. It must be 1/2 somewhere. Where's the 1/2 coming from? Oh, because we have 2. Oh, we have an X. Oh, these are not the same states. So this one should be P squared. What is our should be a p squared, so this gets 2 there. How do I get the half? I want to see this becomes 1/2. This wouldn't become 1/2, would it? Oh, now we have x over p, so it's not just a Gaussian. I don't remember what this one is. Let's just look at the answer. What did they say? Okay. X1 squared is p divided by 2. This should be 0. 3p by 2. Well, how the heck is this supposed to be 1 then? Oh, they changed SD. Oh my god. I wasn't paying attention to that. For symmetrical, what do we have? Same thing. So these parts are going to stay the same. So we're going to have 1/2. So now we have contributions of each. So these are just going to be 1/2 and 3/2. So we're going to have 1/2. now we have to do this minus 2x1 x2. And we just need the and then this is e to the negative x squared. Yeah, I'm going to write the whole thing out. I'm trying to take shortcuts, and I don't think it's good for me. Minus all right. Let's do the first part. Which is b e to the minus x squared, but this is x1 and this is x2. So this will be 0. So there's going to be 2 zeros and then 2 cross terms, because we have these two. This one's going to be 0. This one's going to be 0. But we're going to have this one plus this one. So I think we're going to get a factor of 2 out of this. And these are going to be reversed. So this is going to be 2 and this is going to be 1. And so these are still going to group. I should have x squared, x1. So I think it should be this. So that should make our answer for S equal to 1p squared, and for the should be equal to, again, 3/4 p squared, 3/4 p squared, and then this is now minus. So it's going to be now. How do I get half there? That's not 3/4 and 3/4. It would be 1/2. I think it's this has to be 1/3 and 2/3. Oh man, I have no way of knowing where I need to go. What are we doing here? All right. Number 2. And then these experience different forces. So the anti-symmetric case, because of the interference, experiences a repulsive force, and the symmetric case experiences an attractive force. This is a good exercise. C, plot the probability density so associated with each of the 3 wave functions as a function of x1 and x2. So let's try to draw that out. All right. So let's go distinguishable. And these are Gaussians. One of them is a Gaussian and one of them is x times a Gaussian. So let's just go Wolfram alpha right now. Okay. And then x1 is what? This is just a Gaussian. should be centered at the origin like this. And they should have the same height. So let me just do it this way. So these are the Gaussian, but the probability density is going to be 2 times this, or this squared. So I think it's going to correspond to a more sharply peaked thing. And then this guy is going to be like same thing. So let's just draw it as like a, so here it's going to be very likely so we're experiencing something like and it should taper off here. So we have something kind of looks like it's kind of concave. This is our probability function, right? In 3D. And then if we were to do the but this time our thing is symmetric. So we have to have contributions from both. So this one is this. This one is our this. But this is only half. 1/2 of it. We also have to have plus this one. So this gets decreased by half. And we have kind of this thing going on. And then it's got to be and then these two things combined. It's got to be right like that. And so what does that look like here? So there'll be a dip here corresponding with this. This is also going down. And a hard shape to draw. It'll give me kind of a lump here. And then it's going to kind of go it's going to look kind of like this, I think, with look kind of like that. With this being a kind of similar point. So this is what my symmetric kind of looks like. Like that. And that's the anti-symmetric case. The anti-symmetric case is that on this side we're going to have this minus this. So we're going to get something like that. And then on this side, we're going to have the opposite. We're going to have this minus this. So we're going to get something like this is going to be the so let's try that here. And then this one we're going to have so here we're flat. These two interfere. And these two interfere in this region. But where do we get? We get super downward here. So it'd look kind of like, let me just shade this off a little bit. There's gonna be kind of like a hole here. And there's going to be kind of like a little hill here. And then here it's going to be kind of flat. I can't really draw it, but it's going to look kind of like that. All right. Let's do it with Wolfram Alpha and see if we can't get... So let's do z equals e to the squared plus square root 2 times x times e of negative x squared down to y y. See if they can do something. Oh, they generate a 3D graph for us. Yeah, okay. So what I was drawing here, yeah, it's kind of right. So it's kind of like goes up. So I was kind of drawing. Can I rotate this? Yeah. All right, now let's try it with and then this plus this with the variable flipped. Can you guys see this? Yeah, I think so. So this is going to be y, this is going to be x, and x. Maybe I didn't normalize them properly. Oh. No, I didn't do this properly. Did I have too many brackets here? Yeah, I think so. I think this is right. Yeah. Okay, here we go. Why does this go straight out? Let's just graph what one of them looks like, and we'll have the reverse. X times and this one is going to be twice So they should have like a lump like this, right? Should have 4 little lumps. All right, let's look at the answers they have here. So we have I think it's because I was doing the functions, not the probability. That's an interesting visualization, though. So this is the symmetric case, where x is equal to x2, and this is the antisymmetric case. Let's go D. Suppose your lab partner places n identical bosons of mass mu in an infinite square well with L cooling them to the lowest allowed energy state. What is the wave function? Well, if they're bosons, then we know that they're going to want to be in the same state. So those are going to be x1 ... xn going to be equal to, I would say, 1 over root n, the sum of these are going to be infinite well. We can say sine j equals 0. Let's do j. Sine of xj divided by L because that's going to be the wave function, right? They're all going to be in this state, which is the lowest one. It's equal to 1 over root n sum j equals 0, not to infinity, to n, 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 and then this is going to be phi naught x. Energy it's just going to be the sum of all those. So it's going to be n e naught divided by root n, I believe. That's if they're all distinguishable, though. What's the case of them? Yeah, for them being symmetric, what's the case here? Because it's not this. This is just all differentiable. Distinguishable. So what is it going to be? Let's try 1 over root n. Get rid of this 1 over root n right now. And then we have the product of k. Let's say k equals let's go m. M equals psi 0. It's going to be psi psi 0 x of m. I'm not going to do this product because it actually has to change each time, so we have to have all combinations. Is it all combinations? So if we have all of the functions of just, they have to be symmetrical. What does that look like? So it's an n-dimensional thing. So it should just look kind of like that, but in n dimensions. How do we make that symmetrical? How would we get all the combinations of particles? So let's try 2 particle case is going to be So we have is equal to root n factorial. So it's going to look like this. What is the energy? What's the energy we got out of the last one? I have no idea how to calculate the energy here because you have to do it over so many. There's got to be some trick to doing the math here. I actually don't know. So let's see what they did. All right. by 2 be that's just what it is for one particle. I don't understand. For fermions. Choose for fermions. Okay, right. So we have E. E1 F is equal to the sum of, let's do some minus. So E to the F1 is equal to the sum of and what are the states of the infinite wall? Do I have infinite wall here? That's going to be E naught times over pi. Hold on a sec. We want k squared, so that's look at this. So it should just be e n plus 1 squared. And then the delta E F is going to be equal to e to the n plus 1. Right. It's e to the n plus 1 minus e to the n, because we're only lifting only one level. Okay, well that one, the solution made a lot more sense, even though I was stuck on the... this is problem 5. Meaning of the crystal momentum. Let's go here. Problem 5. Consider an electron in a periodic potential with energy spectrum EQ in a wave packet with crystal momentum HQ propagating with the group velocity Vg is equal to 1 over h bar dEq over q. So suppose a force acts upon our system. Use elementary physics like conservation of energy and the fact that E is a function of Q to show that dHQ dt is equal to F. What do we have here? I think this is a little bright. I'm going to try to make it a little bit easier to see my screen right now. I'm not quite sure why this is so blue. Oh, now we're getting it. So, all right. dHQ dt is equal to F. Okay. So our group velocity, this is a lot of 803, which I have not done. So it's a h bar 1 over h bar. Suppose a force F acts upon our system. Use elementary physics like conservation of energy and the fact that E is a function of Q to show that dTHQ is equal to F. What do we have for basic physics here? Well, energy is equal to force times distance. What other things can we prove? Taking the time derivative of it's equal to a force. What length? How do we show that dq? Well, if we take velocity group is equal to 1 over h bar. And I want to get this into velocity is equal to d next group dt integrate over dq, integrate over dq. There should be q dxg t equal to over h bar h bar q 1 over dxg dt. No, this is just EQ. Hold on a sec. This is going to be EQ. So we have H. Q is equal to 1 over E time of E. With respect to time, HQ, and we get I really need to put this in here. So this is velocity. This is going to be the second derivative 1 over the acceleration. Derivative of 1 over the velocity. Equal to there's no time terms there. Q depend on time? No. The group velocity is a constant. Let's try a different route. What other things can we try? Let's just maybe I've got a formula here that'll. No. Conservation of energy just means energy is not going to change. D. EDT. So we already. All right, let's try this again. So we know we have a force acting. So PG is going to be equal to this whole jazz. So we take D dt of Vg at 1 h bar. That's another way I can show this. we have a force acting on the system. So dHq T is equal to the energy over the acceleration. How do I get this into a force? Is energy over an acceleration equal to force? Force energy over distance. Over x is going to be minus. Your velocity squared. Hmm. You know what? Instead of looking at the answer right now, I think what I'm going to do is switch over and I'm just going to take a little break. I think I'm going to probably be back at 3, and then I can do another 3 hours from then. Maybe if I give myself a little bit of space, I'll come back at this problem. I'll be able to finish it. But overall, I'm doing pretty good. We've got, what is the question? This is 5. So this assignment is going along fairly quickly. And I'll be through it probably end of the day or early tomorrow morning. Maybe early tomorrow morning. This question 7 is super long. Probably tomorrow morning. And so if I can finish this tomorrow morning, then tomorrow afternoon, I can start making the full assessment. And then it'll just be an issue of how much can I practice all the component skills, all the component concepts. Do I want to redo some problem sets? Do I want to do different types of practice? Like, how do I want to get better at those things? Do I want to go back and selectively relearn some sections that I'm a little confused by? So just stuff like that. So I'm going to take a little break right now, and I will be back in about half an hour.